Cilinder bij ons gebruiken, daar zit nog 50 bar op of zo, denk ik.
Ja, het is even tijdelijk om, anders gaat het weer dood. Dan krijg je weer het,
Alright, okay, good afternoon everybody. It's very nice to present because now we have just eaten, so everybody's satisfied. It's going to be more fun for us. So our project is called Non-Destructive Screening of Polymer Systems. The group members are Adriaan, who's not here because he can only come on Wednesdays, he lives in the city. Me, Daniel, Gijs, and Thomas. And here is the summary of what we're going to show today. So we are going to show a little bit of the division of the project, then the motivation that came and our goal with that, the hypothesis that we are based on, and for this we need some background information from chemistry and from physics a little bit. We are going to tell a little bit about our approach, how we are going to solve this problem, how we intend to solve this problem, and then how this project is divided into a chemical and a physical part. And then questions, please, if you have, just keep the slide and we can solve it later. All right? So let's go. The project is divided as follows. Our team leader, Karl, is not here, is here in Curaçao having fun on the beach. The chemical part, we have two chemical engineering students, Gijs and Thomas. Sorry, Adriaan and Gijs. And the physical part is composed basically by Thomas and me. The motivation and our goal. So our project is for a company, and for that it's confidential. So there are lots of things that we cannot tell you, like deeply. And there are also some words that I have to avoid using. So I try to make it as possible as less confusing and more understandable for you guys. This company works with some kinds of polymers, which we cannot tell which, but basically this company wants to guarantee the quality of the production line of something that is made based on polymers. And for that, we have a hypothesis, which is the use of an optical fiber. We could use it for measuring the strength of that polymer. It might sound a little confusing now, but maybe later you understand. So, okay, so that's our hypothesis. And as background, we needed some background for Karl Robitzer's thesis, which is also confidential and cannot go into details, but it's also based in polymers. And we need some chemical background about polymer analysis, which those guys who work with chemistry have. And the physics part, we need some background on optical fibers. I don't know how much you know about optical fibers, because for physicians it's a very basic concept. But I don't know if I really need to go into details. But does everybody know how optical fiber works? Okay, so let me explain. It's mainly based on the principle of total internal reflection, which is you have two different media with different refraction indexes. And when we have like one light or one wave, it doesn't need to be light, one wave coming from one medium into the other medium, when it reaches the surface and it reaches a different refraction index, it's going to be reflected and refracted. A part of it will be reflected, and what we're showing here, it is going to be refracted to the other medium. And then what happens? For example, if you have this angle here, this green angle, we have a small angle, and then so we have a small angle and then the refraction like this. As we increase the angle, we have a bigger angle, and then as the bigger we have the angle, so the more there's a limit angle, which is here for this case. We are considering the glass and air as the two mediums. So we have this limit angle here, which is the base of the red drawing here, and then any angle which is bigger than this one, it will cause a total internal reflection. So for this we need two media. One needs to be the more refringent, needs to have a bigger refraction index, a higher refraction index, so that this can happen. And we basically have the construction of an optical fiber. It's basically on this here we have a core, a cladding, and an outside jacket. The core, and the interesting thing is that the core and the cladding are made of the same material, are made of silica. The only difference is that this silica is different from this one. The refraction index of this one is a lot Not a lot, but it's a little bit higher. It's a little bit higher than this refraction index of this material here, this silicon. And this is an outside jacket just to protect. Well, this is the basic concept, but from this you can have many intermediate layers depending on the kind of fiber that you are constructing. And here, these fibers are basically divided in two types of modes. You have multi-mode fibers and single-mode fibers, which basically are, you can divide them considering the size of the core. Yeah, the size of the core, for example. When you have a bigger core, you call it multi-mode fibers because it allows multi-modes. What does it mean? You can have, for example, a LED, an LED as the source of light, and many modes, many wavelengths can travel inside. But as you make it shorter like this, you have a single mode fiber, it allows only like one mode, one wavelength. So necessarily you need to have a laser as a source of light for this case. Okay, and for our approach, we are choosing the single mode fiber because we are going to work with a laser as a source of light. Our approach is to use this fiber embedded into this polymer, and for this we need we have like in these 2 previous months we have had lots of not lots but some approaches, and one of these was to work with a naked fiber because basically we need this light to get in touch with the polymer. But we can't do it like with a normal fiber because the normal fiber is built of 2 silica compounds, and the light will only travel in the inside, in the core of the silica. It will touch the outside, but it comes back reflected. So it will never go out, never leave. And then we need a different kind of fiber. We thought of the naked fiber, but naked fiber is one that used to be built which doesn't have the outside, the cladding, only the inside, but it's not, the limitation was that we did not find it, it's very difficult to find. So we thought of a D fiber, which is something like this. We kind of put some chemicals on it, and it becomes like this, like it's part of the fiber, it's, how do you call it, it's etched, yeah? We etch this kind of fiber here, and then it becomes like this, and you can see that we have here the core, again, we have here the core, and the outside cladding here of silica is shorter in this case. So the evanescent field, which I'm not going to go into details, but the evanescent field here is possible. It allows the wave to go out and to get in touch with our material, with our polymer. So our approach, we need to make our own D fiber because we need a D fiber, but with a specific kind of material outside. We are going to use fiber Bragg ratings, which is a concept that Thomas is going to show in his presentation. And we need this fiber Bragg ratings in a D fiber, so we need to compound both. So that's what we're going to build, so that we can make the experiment. Then I'm going to invite Gijs to talk a little bit about the chemical part.
Okay. So we need to have a D-shaped fiber, and they were made by a company, but the company doesn't exist anymore, so we have to create one ourselves. First a little bit, we're going to do that with etching, so first a little bit of background information about etching. You use etching with your starting material. Basically you throw in some kind of acid on it so that it erodes. But to make a certain shapes in your material, you want to put a mask on it so that you want to put a mask on it so that it etches only in the area where you want it. So you mask this, so this won't be etched, and we'll go in between here, and you might get something like this. Now you have 2 types of etchers. This is isotropic, it will go in all directions, or anisotropic, it will go in one plane only. So that's some background information about etching. To do our D-shaped fiber, a fiber is very small, very thin. We have to make a container. So we went to Kevin, who helped us design a container with SolidWorks. This is the design. So this is the cup with the etching solution will go in here. It's HF in this what we're going to use, because HF is widely used for etching fibers. So this will be filled with HF. This ring here is for concealment. A rubber O-ring will go in there to seal it tight up so there will be no leakages. Then we have the lid. You have the stripe here. It's a little slit where the fiber fits in. So we actually don't need a mask because the lid itself provides protection at the sides, so only the top side will be etched. Of course, this container needs to be made out of material which won't be etched away. So this is why we use Teflon, so this HF resistant. For the actual making of the fiber, we will have to do a number of experiments, a number of repeatings. We will use different HF concentrations, and we will have to test what is the best time and the best concentration to use the desired result, so that we get the D-shaped fiber with the correct distance. So now Thomas will go on with the physics part.
So for to assess the strain and temperature qualities of our fiber, we want to perform some experiments which have already been performed by Jan et al. In an article they wrote, and what we basically want to do is recreate their experiment and using other variables to get that information on strain and temperature. What we want to use is fiber Bragg rating. Fiber Bragg rating is is periodic or quasi-periodic variation of refractive index in the core of a fiber. As you can see here, you see the gratings, which have a different refractive index from the regular core. Those gratings, they serve as they act as a wavelength specific mirror. As you can see here, the input in the fiber, a part of it will be transmitted, and a small part will be reflected. And this small part is sensitive to strain as well as temperature. Jan et al. They use this sensor to measure the sensitivity of a photonic crystal fiber. Photonic crystal fiber is a very asymmetric fiber, which is asymmetric in the core, so that when the light is reflected, it can detect changes in strain and temperature apart from each other. So there will be a measured difference in strain and temperature reflection. A normal fiber doesn't distinguish between this reflection. So as long as the strain and temperature coefficients of both polarizations aren't equal, then you can distinguish between strain and temperature via this matrix. So what we will be doing is repeating the experiment by Jan et al. And they used a polymer foil to guide the fibers through it, and we will be replacing that foil with our polymer. Any questions?
Are there any questions?
You want to use the evanescent field to cure the polymer?
We are going to facilitate it. How is it? Okay. I just mentioned the evanescent field, so to make this answer more clear, the evanescent, it's like when the, if you allow me, when the light touches the surface, it's not that it doesn't go into the other medium. It goes a little bit. This is the evanescent field. It's the amount that surpasses to the other field, to the other medium, but it's attracted by the medium back, by the medium which has the more refractive index. And then the evanescent field is very like it's the scale of nanometers. And in a normal fiber, you never reach like to make this light, to get this light, to point something on the light. What you're trying to do is to measure, as we can handle, for example, making D fiber in a fiber fiber graph, for example, and then we are going to use the evanescent field. Karl can correct me if I'm. Can you listen to me, Karl? We are going to measure the evanescent. By using the evanescent field, we are going to put this light in contact with our polymer. Am I correct?
That is to initiate the curing of the polymer. Or is it going to cure the polymer itself?
I cannot say anything about curing because as our project is confidential, so if I go into this kind of details, I'm going to speak too much and Karl is not going to like it. But it's on the way.
Okay, so as long as you know the evanescent field is just a few nanometers, you cannot cure it, you can only initiate the polymerization.
Only initiate. Because
and you will use the temperature to monitor, another fibers to monitor the temperature while it is being cured. Right?
Yeah. Because as we are going to make the D fiber, then we are going to put like almost to break, almost to destroy the outside cladding, and then there will be only some micrometers, some nanometers resting, so it will be possible to kind of have the evanescent field.
All right. So I will assume that you will have fiber, which is stripped as you showed. You have your asymmetric fiber, which has a evanescent field from one side.
Yeah.
And I assume that you're going to initiate the total reaction this way. What I want to mention only is that if you are going to strip fibers and come close to the cladding, and you're going to manipulate the evanescent field, you will have actually a photonic fiber. Yeah, what you showed, with the etching, you will create an asymmetric fiber, a photonic fiber. It is important to know at this stage that you might also not get any light through it, especially if you're using a single mode fiber. It will may happen that you are not going to have any light propagating through it. So it is you have to be actually using, from this point of view, a multimode fiber where you have much less sensitivity. So I suspect that if you're using single mode fiber and you indeed have this very controlled way of etching the cladding from one side so that you have access to the evanescent field, the presence of this polymer there will influence the propagation of light, and it may happen that light doesn't propagate.
You mean because of the gratings or because of the shape of the
because of the interaction between the light that exits the fiber that you need to initiate your catalysis, your polymerization. Yeah? It may happen that it will just propagate for a few centimeters, or maybe less, or a millimeter, or a micrometer, and then it's gone. You are creating actually a multimode fiber from a single fiber.
Yeah, it makes a lot of sense.
So this is something that may come up if you indeed do experiments. That you may want to consult somebody else that has more experience with fiber.
Okay. Thank you. Any other questions?
Are you creating a break kind of reflection?
No, we are going to have
Or
one.
is it something you buy? Or
Yeah, we can buy, and we are going to make it become a D fiber. We're going to make some mixture. We have D fiber, we have brag fiber, but we're going to make like one over the other. So that you can have specifically what you want to measure.
They probably want to measure the temperature as they are curing the devices inside.
Yeah. Any other questions? Okay. Thank you.
One question. The fiber is attached to the lid of your
Yeah.
container. How is it fixed over there?
Okay. This is more the chemical part I try to say, but you correct me if I'm mistaken. Because he and Adriaan are working kind of separately with this part of the chemistry of building this. And as I understood, the fiber will be attached here. It will be like, can I explain how?
Yeah, that's still the tricky part.
Oh, we're still building it.
The idea was that you put the fiber in, then you put the lid with the O-ring on it, and then you clamp it.
Okay.
So because the fiber is sticking out of the lid a bit, the O-ring deforms and clamps the fiber on its place. After that, on the top part, you see a hole. You can insert the HF afterwards.
The O-ring, what kind of
This year for the rubber. The rubber just to
The rubber O-ring, yes.
I'm sorry?
Is it HF resistant?
No.
Yeah, the HF resistant O-ring, yes.
It's not a rubber.
Of course.
It's a seal.
This is the 8F and here is the 8F resistant.
It's not Dora, it's another material. I don't know the name
Carvis. The O-ring is made of Carvis. It's a special type of rubber. Some kind of phyton-like.
Okay, are there any other questions?
Yeah, it's a small question about the leak testing. I hope you won't be testing it with HF if it leaks.
No.
Okay, that was quite a little bit unclear, so I didn't know if we had to prepare for evacuation yet or
We thought about it. Okay, any more? Yeah?
What are any alternatives to using HF or this solution? Because it's not a very nice substance to work with.
Specialty chemistry guys.
We didn't search too far because HF is always used for this part law.
Yeah, maybe if you have some problem, if you find some problems by using it, you're going to research a little bit, but not so much. Any other? Okay, we thank you very much for your attention and have a nice afternoon.